Welcome back. So we're thinking about fluid mechanics at this point as we work our way towards a full description of active matter. And in the last vignette, what I did is I talked about force balance, and really that means F equals ma. One cool way to think about it that maybe I'll go into later is that we have often talked about the rate of change of the quantity inside of our material volume element as being the divergence of the flux. And in this case, it's the flux of momentum, linear momentum, that's in play. That's kind of a cool view. But as you can see at the bottom right here, bottom left here, this treatment was force balance in the sense that we figured out the force on all six faces of this cube, and then we summed them up, and that should be equal to ma, and that led us to this notion of the divergence of the stress. So what we're going to do now is we're going to talk about the third step in the continuum theory protocol, which is we need to figure out the constitutive law. And when I say the constitutive law, what I mean in this case is the relationship between the stress tensor and the velocity field. So that's the connection that we need to make at this point. So just as a reminder, last time we did this force balance business, that was cool. And the thing I wanted to note is that we already achieved the left-hand side, which was our force balance statement. Now what I want to do is I want to talk about the right-hand side of this diagram, which is the constitutive law for a Newtonian fluid. So when I talk about a Newtonian fluid, what I have in mind is really illustrated here by this experiment, which I'm going to read you straight out of Newton in his Principia, in the second book of the Principia. But let me just give you a sense of this. The idea is that we have this thought experiment where we have a fixed plate that you can see here, and then we have a second plate right here, which is moving at a speed v naught. And the question is, what are the forces that are produced inside of that medium between those two plates? And what we're going to end up saying is that the total stress, so I'm going to write that at the moment as a matrix, is going to be given by this expression, where this piece is the hydrostatic stress, and I'll come back to that in a moment. And this piece is the strain rate tensor, and that accounts for effects like the one I was just talking about, which is the velocity gradients. So in elasticity, remember that I made this big deal about how an interesting deformation was one in which there was relative motion of the points within the elastic medium. And the same is true here. It's just that instead of measuring relative displacement, we're measuring relative velocities. And so as you can see here, the rate of deformation tensor, for the simple case in which I have a gradient in the x1 velocity as a function of the x3 coordinate, yields the rate of deformation tensor that you see here. So let's say a little bit more about this from the standpoint of phenomenology. Where does this particular result, this one, which is what I just wrote down, where does that come from? So first thing I guess I want to say, let's take a look at this. This is from Colin Pask's quite amazing book, and I'm just going to read you the whole thing. So finally, we come to what many people see as the rationale for the whole of Book 2, that is Section 9 of the circular motion of fluids. It is here that Newton attacks Descartes' vortex theory of planetary motion. So, this is one of those things that's forgotten, but that there was a notion, wouldn't call it a theory, a hypothesis of Descartes that, just like you see in your bathtub, a piece of dust or something goes like this in an orbit before it goes down the drain. Descartes had posited that the motion of objects in the celestial heavens was the result of vortices. Descartes gave no explanation for how his vortex theory could lead to Kepler's laws for planetary motion. Newton took up the challenge with the aim, of course, of discrediting Descartes' theory. This is a difficult area of fluid dynamics, and Newton was well beyond his capabilities to discuss the problem in mathematical detail. It is interesting to note that here, for the first time, he makes some assumptions about the way viscosity enters in order to transmit fluid motion from one region to another. He introduced a hypothesis. The resistance arising from the want of lubricity in parts of a fluid is, other things being equal, proportional to the velocity with which parts of the fluid are separated from each other. So that's archaic way of saying the velocity gradient. This has now become the standard way to relate shearing stress, viscosity, and velocity gradient. Fluids behaving this way are in fact known as Newtonian fluids. And so for my purposes, that's described by this experiment, which I just showed you, but now I'm kind of giving you the actual constitutive relationship. So note that the shear stress that I'm talking about, remember that this is the force in the x direction on a plane with normal z. So I would call this sigma 1,3. So that's another way of writing this according to how we wrote things earlier. So sigma 1,3, and this is equal to minus eta dvx by dz. So it's telling us that the larger the gradient in the velocity, the larger will be the shear stress. And the way that I want you to think of that is that the shear stress is tending to equalize the velocity. It's going to slow down the fast motions, it's going to speed up the slower motions and equalize them. And there's a really nice and kind of fun kinetic description of this where you could think of two trains on frictionless tracks parallel to each other with their boxcar doors open, and I have a sandbag and I throw the sandbag over to the other train, and what that's going to do is that's going to transfer momentum from one train to the other, and that's really what this is about. That's why I was saying it's a statement about momentum transfer. So with all that said, let's now just kind of take a tour of the stress tensor. So the first part, I said that sigma is equal to minus p times the identity matrix plus 2 eta d, where d is the rate of deformation. So let's start by thinking about this piece, which is the hydrostatic piece. So this is one that we're all used to. If you take a water bottle up in an airplane and you open the bottle at altitude, then when you arrive at your airport of interest, you will find that your bottle is being crushed. And similarly, if you open the bottle at sea level and then you go up in the airplane, and then when you open the bottle, you hear it hiss because there's a pressure differential between the interior and the exterior. So we're all used to this, and I just want to show you that the sense in which you're used to it is reflected in the mathematics. So here I show you this is the conventional potato of continuum mechanics. Here I identify my material volume element. And what I'm claiming is that the state of force on the material volume element is described by a series of inward pointing vectors. They're normal to each of those faces. And so sigma ij is defined as the force per area in the ith direction for the face with normal in the jth direction. So here, what that means is that, for example, this face over here, that's a face in the one direction, and the only component of force is going to be in the one direction. So that means that the only piece of the stress tensor which is non-zero pieces are going to be the diagonal pieces. Sigma 1,1 is going to tell us about the forces on these faces. Sigma 2,2 is going to tell us about the forces on these faces, and sigma 3,3 is going to tell us about the forces on the top and the bottom. So that means that, and there's a minus sign here because the force is inward acting. Remember that sigma, if I want to find the force acting on such a face, then the force per unit area is sigma ij. So I know that the force is in the negative direction on the face with normal pointing in the positive direction. So that's the reason for the minus sign. And so effectively, what you see here is what's often known as Pascal's law. So we see that the hydrostatic stress tensor is diagonal, and it is its points inward, as I already said, And I remark that the identity matrix or the identity tensor is given by this nice diagonal 3 by 3 matrix. And finally, in additional notation, I can write this in this way, where I use the Kronecker delta, which is defined by this property. In other words, it's a 3 by 3 matrix, which is the identity matrix. The Kronecker delta is a nice compact way of representing the identity matrix. So this is how I can think of the hydrostatic part of the stress tensor. Very useful, because as you're already anticipating, we're going to have to take the divergence of the stress tensor in order to work out the force balance, and so we'll need that. So I've already commented on the rate of deformation, and so in general, the rate of deformation tensor is given in direct notation by the gradient of the velocity plus the gradient of the velocity transposed. That basically means that I change the order. So, this in additional notation, this is what that instruction means. So the rate of deformation tensor, dij, is given by 1/2, and then dvi by dxj plus dvj by dxi. So it's properly symmetric. And so if I want to write out the full rate of deformation tensor, I can do that as shown here. So this is basically how you write it in component form. So from this point on, that's really a matter of turning the crank. What I mean by that is that's the definition, if you like, of the rate of deformation tensor. So if you have doubts, if you think, this is messy or whatever, you can think of it for the moment until you get more used to it as it's an instruction to compute a particular matrix. And that matrix has matrix elements, as I define here. And those matrix elements, what do they measure? They measure the rate of change of velocity with position. And so a net uniform motion, just like we found for strain, a net uniform motion does not engender any shear stresses. All right, so I already went through this example, this first example. I'm afraid I'm going to lose it. Yep, predictable. You can just tell when it's losing patience. Sorry, just bear with me. I'm in a place with not such a great connection, and so annoyingly I seem to lose my connection to my screen. Okay, looks good. It looks like I've got it back. So here's the example from the classic Newtonian experiment, and what I'm saying is that this separation between the two planes is h, as you see over here on the left. So this separation between the planes is h. The bottom plane has motion 0, the top plane has motion v, and that means the gradient is v over h. In other words, if I want to find out how fast the fluid is moving at a given height, I take this slope dv by dx and I multiply by the height. So that'll give me the v at a given height z. Okay, so that's the rate of deformation tensor in that case. So I think we've basically got ourselves a description of the stresses in a fluid, and I just want to finish with a couple of little observations. So I just remind you that once again that stress has units of force per unit area. If you look back, let's actually take a look at this. So I can use that to compute the units of the viscosity. So that's kind of useful. So on the left-hand side, sigma has units of newtons per meter squared. And then dv by dx has units of 1 over seconds, right? Because velocity has units of length over time, and the z in the denominator, or the x in the denominator, has units of length, so we're left with units of 1 over time, and that all implies that the viscosity has units of Pascal seconds, or newtons per meter squared per second, times seconds, sorry. Typical value, so eta for water, this is worth carrying around in your head, is 10 to the minus 3 Pascal seconds. So that's a value that we will hold on to and use ourselves. So this is what I wanted to say about the stress. Now what we're going to do is in the next vignette, we'll derive the governing field equations. That's where we are.